Okay, just making sure this thing works. So far, I think it's gonna be okay. We're gonna see what happens when we start scrolling down. Okay, so chapter 21, alpha carbon chemistry. I like this chapter because it's one of the first chapters that kind of introduced like diverse kind of carbon-carbon bond forming reactions, right? Generally, the only really three carbon-carbon bond forming things you've learned is the first one is Grignards, which are still extremely used today. Like people still use those to this day. Wittig reaction, which is also a very useful reaction. Then I guess Gilman would be the third one. I don't know if there was, I guess you could kite cyanide as well, but you know, functionality is a little bit limited there because of the nitrogen. But here we basically can create carbon-carbon bonds using kind of exploiting the property of carbonyls, right? So let's start with some practice problems. Okay, so 21.4. Okay, so far so good. And the colors are just so washed on the screen, it's crazy. Yeah, so I still had my old Surface pen, but that thing was super buggy, so I found another stylus that I had that seems to be working okay right now. All right, so it says draw both resonance structures of the enolate formed when you have the following treated with a strong base, right? Okay, I mean, this is kind of straightforward, right? All it's really asking you is to draw, I guess, the O- form and the carbanion form, C- form, right? So let's say we have any base. We use NaH, so H-, right? Let's use different colors. And here begins the first part of this bugging out. Oh, damn. This will be a long session. Go. Yep, here it goes. I think I just have to avoid putting my hand on it. It's probably what it is. Okay, and then it has a resonance form, right? If we just kind of alternate this negative charge, right, between the oxygen and the carbon, it would just look like these red arrows. Well, actually, hold up, my bad. I messed up that arrow. Should be this way and then this way, right? Okay. I think both are acceptables in terms of what you want to do if you're ever given yeah, I had thought about that, but the thing is, realistically, I'm probably just gonna go to the Microsoft store next week and just buy the Surface Pro 8. Like just a few days of using an old laptop has annoyed the shit out of me, where I'm just willing to shell out the money for a new one. Because the thing with the Surface is you don't need that kind of hand stuff. The pen works so well with the screen that I literally rest my hand on my screen and it won't detect anything but the pen. It's just so nice. But anyway, so back to this chemistry here. So one thing is, which one is the more significant contributor? I guess if we label these A and B, maybe easier to describe. as Muhammad's there said, right, it's A, right? So this is just one thing to kind of understand. And it's generally why I like to draw it in the O minus form, because it makes more sense that, I mean, even though the chemistry occurs through what's called the C attack, right? The A minus form is how you'd probably, I mean, obviously resonance structures, they aren't real, but they can just kind of give us an idea of how it probably acts, right? A is more significant because the O minus, the O has a negative charge, right? Generally, we don't want carbons to have negative charges, right? So I think in terms of mechanisms, if you are given like an enolate type mechanism or something for your third exam, right? I don't know, what did he say in class? Does he care if you put it in the C minus form or not? Is he okay with both forms? Does he want it O minus? I think the main thing he's looking for is if you understand where the electrons are and all that stuff. But did he mention in class? He draws both. Okay, that's perfect then. Yeah. So like as long as you understand what you're doing and you understand really what's formed, right? The whole purpose of this is that we have a pretty good nucleophile here, right? Right. And the whole reasoning for this, right, is that these protons, right, they're partially positive because of the electron withdrawing effect of the carbonyl, right? This is why I kind of wish they taught like acidity like this in terms chapter 3 when you learn it in Orgo 1, because you kind of just learn Ario, right? But you got to understand, like, that's why the I part in IO, the induction, right? They shouldn't just include halogens. They should include all electron withdrawing groups. And then people would, from Orgo 1 understand that, alpha protons are acidic next to carbonyls, right? So yeah, the rest of these problems, well, actually, let's just do C. I mean, nah, let's continue on with actual stuff. So the other ones are just basically just draw resonance structures of all of these. So feel free to do those. It's just really, I just want to kind of introduce some chemistry there. So, okay, let's do 21.8. Start with that. Oh, well, I guess I'll talk about it during your exam during the break. Okay. So H3O plus, it's in the brackets, which means it's a catalyst. And we have pyridine, right? Second step, pyridine. Okay, so what kind of reaction is this? We have in the first step, but okay, before we even kind of, like that's why I said, even if you don't remember it, you can kind of piece it together. When you introduce a ketone to aqueous, like, or acidic conditions, what are you going to form? Enol or enolate? Under aqueous condition, I mean under acid conditions, right? So remember, just to kind of go over the two forms here, right? If under basic conditions, right, we form something that looks like this, right? O minus, and that makes sense too, right? Because we're under basic conditions, there wouldn't be any proton on the oxygen, right? And that could resonate and look like this, right? And in terms of, kind of charges on a species, right? It makes sense because we have negative charges in a basic solution, right? Now, if we're under, so this is base, right? Now under acid, right? If we introduce the kind of acidic conditions, right? What happens first is the carbonyl gets protonated, right? And then eventually water will come in and act as a base and you form an enol, right? So this one thing to kind of remember is under basic conditions, you form enolates, right? Under acidic conditions, you form enols, right? And this resonates like, I guess it would be technically, it's a bad resonance form though, but could technically draw it like this. It's just better to draw it in the enol form because in the nucleophile, the double bond attacks directly. So yeah, so the first thing here, what we're doing, right, is we're turning it into an enol, right? So when we introduce it to acidic conditions, right, we're going to form an enol, right? So we'll have something that looks like this, and this is symmetrical, so it doesn't matter whether it's here or here, right? For the sake of simplicity, I'm going to put it on this side, right? So this is after basically after H3O plus, right? And then when you introduce bromine gas to it, right? Now we have a nucleophile here, right? And this is a pretty good nucleophile because it's alpha to an oxygen, right? So alpha hetero or whatever you want to call it. Basically, it's pushing electron density into this double bond, right? What arrow do I want to use, right? And if you guys remember from addition reactions, maybe from Orgo 1, and obviously you probably just learned this recently, right, is that bromine gas can act as an electrophile, right? So you have a nucleophile, you have electrophile, right? So basically what happens here is you're going to halogenate at your alpha position, right? And that's really what this is just alpha halogenation, right? But it has kind of an added step, right? Which is where the pyridine comes into play. So then if we want to draw out the rest of this mechanism, it's going to look like well, after the pyridine step, when we get to it, I'll talk about what happens here, right? So this goes here, right? We grab this. This just forms Br minus. Let's go downwards, right? And now we have, I guess technically, we would probably have to push electrons because it wouldn't make sense to form a positive charge there. So this would go like this. Yep, that attacks, right? Then your next product will look like this. But Br here, missing a alkyl group there. And there's a plus sign here, which makes sense. It was neutral, gained a new thing. Obviously, it's going to have a plus charge on oxygen, right? We could just deprotonate that. Doesn't really matter what deprotonates it in the first step, right? So I'm just going to say minus H plus. And then you get something that looks like, oh, oops. Like this, right? So this is all after step one. Right? Maybe I'll write this here after step one. How did I get the double bond in the first step? Here. Oh, this was just enol formation, right? So maybe if I go into detail for that, right, is, where's, I got some space here. So if we had this, right, and you had HOH2, oh, I missed that eraser feature. OH plus. Gotta keep my sleeve on the screen. Like this, right? And then you have a intermediate that looks like that. And then what happens here is you have an H here. You could just say water or something came in, right? This is all just when you're under acidic conditions, right? This is what happens, right? So now this is going to do that. That's going to do that. And that will lead to your product there. Right? So that's just enol formation, right? So that's, I guess, two of the things you got to remember from this chapter in terms of just basic mechanisms is the formation of an enol and formation of an enolate, right? So that was a formation of an enol, right? Maybe later I'll just go over the enolate one as well, right? I think I did it in the first step. Yeah, okay, no, I did enolate here in 21.4, right? Those first, when the base kind of attacks, that's just a simple enolate formation, right? Enol formation is just a little bit different, right? It's all like basically think about what you're doing, right? If you have a strong base, it's going to go attack a proton, right? If you have no strong acids, right, then your carbonyl will act as a base, right? So, but essentially in terms of kind of, they're kind of synthetic analogs, almost enols and enolates, right? And then they're tautomers of the original carbonyl, right? The tautomer essentially, right, is just basically it's kind of a difference in a proton location if you think about it, right? That's all really what a tautomer is this kind of proton is in a different place. So anyways, back to this, right? This was all after step 1, after step 2, right? What do we have here? We have pyridine, right? So pyridine is a nucleophilic or non-nucleophilic base? So does it act as a nucleophile or does it only act as a base? Think about that. Base only, right? Because it's too sterically hindered. It's too big, right? To act as a nucleophile, right? And we know its lone pair is outside of the aromatic ring, which is why it's a pretty good base, right? So what happens here is essentially an elimination, right? And you're going to grab the next most kind of a what? So why can't we do the same process and substitute? So you actually can, and that I believe, I want to say it's called the HVZ reaction, or chloroform reaction. I forgot which one it is. Haloform, chloroform, which one? One of those. Yeah, so but that's under basic conditions, right? That's basically what happens is that when you have a strong enough base, right, then you're going to keep deprotonating those extra hydrogens, right? Yeah. The HVZ reaction, I forgot which one that occurs. I think that uses a Lewis acid. We'll probably get to those after this. Let me just scroll down the textbook to see where they are. Yeah, alpha bromination of carboxylic acids, right? The HVZ reaction. And then we have haloform reaction, right? So that's under basic conditions, right? So the main reason here, right, is why more BR doesn't install is because we're under acidic conditions, right? So it's going to be hard for us to remove additional protons, I guess, if you want to think about it, right? Because we have an abundance of stronger acid there, right? Anyways, this is now just kind of a simple elimination process here, right? Just can take one of the protons off of here, right? So say this drops here, right? This is gonna here and then kick that. Basically an E2-like elimination. Hey, did you guys learn about E1cb yet or no? It's kind of a new type of mechanism. Similar to E1, but okay, so it looks like we're probably gonna get up to probably around Clayson. I was looking at your lecture, and it looks like you guys ended around Clayson's. Okay, so after all this, maybe let me draw this a little bit neater for y'all. Right, so nitrogen grabs the H, gives back its protons, form a double bond. Br is a good leaving group, right? And that's why this kind of elimination happens here, right? It's our arrows. And we get a final product that is alpha beta unsaturated ketone. So our final product. Okay. That should be our final product, right? So really you could have two outcomes from this kind of whole problem we did, right? If you were just given only step one, your final product will be the alpha halogenated product, right? So after step one, you would just stop basically here, right? And then after step two, right, when you introduce another base, right, or at least a non-nucleophilic base, right, you're going to basically perform like an E2-like reaction, right? Because we have a good leaving group, we have protons that are slightly acidic next to it, right? So the base can come in, take those, right? And it's going to want to form a alkene there, right? So this is called a alpha, right? Because this is the, sorry, this is alpha, this is beta, right? So this is called an alpha beta unsaturated ketone, right? That's how you describe this kind of product here. Okay, HVZ reaction, right? It's also kind of simple, right? Really, when you have Br2 and phosphorus tribromide, right? Basically, you could halogenate carboxylic acids, right? So actually, the first step, right, is kind of analogous to forming. Well, it's not like SOCl2, but basically, if you have a carboxylic acid, put it in the presence of phosphorus tribromide, or even I guess PCl5 would work for chloride, or there's probably a lot of stuff you could do, but you basically form an acyl bromide, right? And then that tautomerizes, right? And then you can basically install another halogen, right? And then finally what happens is that when you hydrolyze it, it just goes back to a carboxylic acid, but your bromine remains. It's a pretty useful thing because it basically gives you functionality right next to a carboxylic acid. So let's do an example of this. Yeah. 21.10. So I guess I'll show you guys the intermediates. I mean, the book does it too, but I guess on this specific problem, right? Like literally right above this, the book shows you all the intermediates, right? But I will just, I guess, do it for the sake of clarifying what this goes through, right? So H2O. Okay, so we have a carboxylic acid, right? And then you have bromine gas, phosphorus tribromide, right? Followed by a workup essentially, right? So after step one, right, the first thing that's going to happen is the PBr3 reacts with your carboxylic acid, right? And you're going to get a acyl bromide, one of many ways to create acyl bromides, right? Next step is going to be a tautomerization, right? So basically what happens here, right? I guess you could say, right? that H is going to move to where the O is, and then the double bond is going to move between those, right? So that's just a simple. By the way, did he say in terms of mechanisms, it's okay to just write tautomerization instead of having to draw it out? Like if you're going from an enol to ketone or something like that, or enolate to ketone, carbonyl, I should say. Is he fine with just showing, like writing taut or something like that? He didn't mention. Yeah, okay. Well, I guess it also depends if that's a question you'll get asked on your whoops. Let's try not to draw extra lines to confuse people. No, this is not going too bad. Like Thursday, it was horrible drawing a lot of stuff. I think it's just that old Surface Pen was just garbage. Okay, and then this kind of, the book doesn't show this part of the mechanism, but essentially what happens is this is going to, we'll just kind of mention it here, right? Acts as your nucleophile, right? As nuke attacks BR2, right? Let me try to write that a little bit more neater, right? And then, you know, attacks BR2, reforms your carbonyl, right? And then you'd basically get something that looks like this. Oh, oops. So if we introduce BR2 here, right, that's what basically is happening, right? Nucleophile, BR2 installs at the more substituted position, right, in order to basically reform our carbonyl. And it kind of makes sense that this carbon here, right, let me mark it, right, this carbon here is more nucleophilic, right, because if this is an electron donating group, right, this is going to donate electron density in here, right, and make that carbon more nucleophilic. Right, so then our final thing before we get our workup done is this going to actually be another acyl bromide, but halogenated. And then the workup part, which is literally if you just run this reaction and you literally just spray water into it. Not spray water, but you're just going to fill it up with water, and then you get your final product. That's what workup really is. Right, so now this is in its form, and then the last step is just hydrolysis of a acyl halide. In this case, it's a bromide, has similar reactivity to acyl bromide. It's slightly less reactive though, right? H2O. Yeah, so even if you see H plus H2O, the whole point is like whenever you see those as a second step, it's just called workup, right? So in terms of like lab stuff, it's usually when you have something that's deprotonated, right? And you're just introducing a proton source. Yeah. So the last step here, and this is our final product of this reaction. I just wanted to show all the intermediates because I don't know if the book does or not, but just for the sake of doing it, right? That's going to be your final product, right? So whenever you see those reagents, the phosphorus tribromide, right? All you got to really think about is that it's going to install a BR at this alpha position here. Oh, goddamn, that's annoying. Yeah, it's our alpha position. Right, and this is very synthetically useful, right? Any halogen there, you could do all sorts of chemistry. You could create an alkene there, do a bunch of other addition reactions, right? You basically have a diverse amount of functionalization now next to carboxylic acids, which is probably useful in terms of, you know, biomedical chemistry, I guess, right? Carboxylic acids, I don't know. There's probably a bunch of pharmaceutical uses for those, right? So that's why it's just like, you know, when you see a lot of these reactions, you're like, oh, you know, if, you know, for you guys, right, people who are probably not trying to be chemists, it's probably like, yo, what's the point of this? I could just do it in like 10 steps or something like that, right? This one is called the HVZ reaction. I think it's like something Zielinski. Oh, well, here, it's literally right in front of me. Volhard Zielinski. So 3 dudes who wanted to make sure their names get remembered. So they all put them on the name. Funny enough, people just refer to as HVZ, so no one really remembers. Oh, he skipped it? Well, shit. Damn. Should have checked that. Okay, well, what about haloform? Did you guys do haloform? No. Okay. All right, let's just skip to aldol reactions then, I guess. Okay. I thought it was cool. But yeah, well, my point being in terms of synthesis, right, is you don't know in the future, right, if you're going to run into things that might require, you know, you to do things like, you know, create a certain bond in a certain way to create, like, I don't know, let's say you're creating some drug or something, right? And that's why having more and more and more synthetic tools is really important, right? Is because we can kind of have targeted synthesis, right, and get really good terms of you know, product yield whenever they're creating something, right? And that's why, like, you know, chemists are always like, there's so many reactions you guys learn, and there's so many more new reactions, is because, you know, people are constantly trying to find better ways to do specific types of chemistry, or not really even more broad types of chemistry, really, right? And that's why there's so many reactions, right? Even though some of them look like they might be doing, you know, stuff that doesn't seem useful, right? But if you kind of think about it in terms of, you know, what it offers access to, that's really what it's about, right? Is being able to give you access to something that can go through a variety of reactions. So that kind of stuff is useful. So whenever you introduce functionalization like that, I think it's pretty cool. Anyways, aldol reactions, right? This is kind of the bulk of this chapter, besides the Michael additions, but I don't know if you guys probably haven't gotten to those yet. This is the stuff that really kills a lot of people. Mainly being because people have a lot of trouble. What is it? I guess people have trouble with drawing the bonds, right? Second chapter book actually shows you a really nice way of doing it. Probably see if I pull out some problems from there. But for now, let's do some kind of simple practice problems with aldol reactions. Let's see. Okay, predict the main. It's got 21.14. Perfect. Probably just do a bunch of practice with these for the rest of the session. So predict the major product when each of the following aldehydes is treated with aqueous sodium hydroxide, right? So basically NaOH dissolved in water, right? Okay. So damn, this is kind of a big one, yo. Right? But then it's basically just said that if you have NaOH, right, water, what are you going to get, right? So really water is just kind of acting as your solvent here, right? And I guess also a proton source. That's really what it is, right? It's a solvent and it's a proton source, right? Actually, I'm not sure. Might have to use some other solvent as well. Because sometimes like this thing might be too big to. I don't know if it'll dissolve in water. But yeah, mostly it's a proton source, right? Because whenever you have a strong acid, right, kind of issue here is that that the final product will be something like O minus or C minus, right? So in order to avoid that, right, we get I think here. Okay, so I'll do the mechanism for this one, and then in the next one I'll show you how to do the. Well, actually, no. The trick is for the. I think it's for the condensation, if I recall correctly. So this is an aldol addition, right? So let me write that over here. This is an aldol addition, right? basically we're just adding two carbonyls to each other, right? The condensation, right? If you kind of think about condensation, right, it's kind of related to like, water appearing on the surface of something. That's really what condensation, the difference between addition and condensation, right, is really just if you have enough heat or if you have enough energy, right, to basically remove water from it, right? So it's another way of basically getting alpha beta unsaturated carbonyls, right? Which is I kind of like the alpha halogenations, right? But I guess they're more toxic to work with because Br2 gas not good. So let's go down this way, and we'll start with OH minus, and we'll grab our proton here. Ugh. Okay, use our red arrow. Right. You know what? I think I'm going to. Actually, I'll just do the O minus form so people are familiar with it. Okay, so now we have a product that looks like, I'm going to abbreviate that group, pH. Wow, there's a lot of little like taps. Yeah, it leaves a, I don't know if you guys can see that on your screen there, but not exactly calibrated well. That's kind of annoying. Yeah, bit annoying because it's basically registering a pen mark, but I'm not even touching the screen yet. It's weird. Okay, it's not doing it anymore. I don't know. Okay, so you have this, right? So now you have your enolate, and now the enolate reacts with the original carbonyl, right? And that's why this is an addition reaction. I mean, you could kind of think about like the additions as kind of like a dimerization, right? Because it's something reacting with itself, essentially. It's not exactly a dimerization, right? But it's like, I like to think about it that, you're reacting two of the same thing together, right? So here, what happens now is we can bring out our original carbonyl. So I'm going to draw this. I'll just draw it this way. H, right? How many carbons do we have? 1, 2 between the cophenyl group. Right, there we go. Yeah, right. So that's a kind of one thing to understand about this is that you have let's say you have, I don't know, 1 mole of your carbonyl here, and you want to get an aldol addition product, right? The theoretical max yield of your final aldol addition product, well, you guys can tell me, right? What do you expect if it's reacting with itself? What's kind of the max amount in terms of moles you'd be able to get of your final product if you start with 1 mole of starting material? Yeah, this is a negative charge. Sorry if that isn't clear. This is kind of just something to think about in terms of this reaction, right? So if you start with 1 mole reacting with itself, theoretical max yield, right? Basically, it's doing half and half of each, right? Half, let's say up to half turns into an enolate, right, and reacts with the other half. So your max yield will actually be a half a mole, right? So that's why in terms of your final product outcome, you might want to let's say if you're targeting a millimole or a mole, okay, let's not use mole. Let's say you're targeting a millimole of final product, you need to start with 2 millimoles, probably more of your starting material, right? Because it's reacting with itself, right? Basically, you're turning an electrophile into a nucleophile, and then they're doing an kind of intermolecular reaction, I guess. Okay, so now you have a powerful nucleophile, you have a good electrophile, and that's what happens here, right? So now if we move these arrows, right, the full arrow movement would look like this, right? Notice one thing, when we are doing all these mechanisms. What did I mention in the first kind of day of class this semester? Whenever we're in basic media, what do we expect the charges to be on all the intermediates? Negative, right? So that's why I said that's going to come back later, and it's very important for this chapter, right? Because you gotta be very careful if you draw a positive charge or whatever. Think carefully, right? Don't do like in terms of your mechanisms or your products or stuff, right? Understand that we're in highly basic conditions, right? If something that's a positive charge or an extra proton or something, right, it's going to immediately be attacked by a base, right? So that's why negative or neutral. That's it. Okay, so now this is the annoying part, right? Is drawing the bond, right? So basically, let's do some carbon counting here. So this is how I used to do it when I first learned it, and obviously during an exam, you try to avoid doing this. So this is 1, 2, and it's bonding to 3, 4. This is connected to 5, which is that, right? So let's draw, I guess, what's it called? Damn. This is my least favorite part is literally drawing this. Um, so what's it called? Let's see. Hold up. Let me draw the original structure first. That's 1, 2, right? Whoops. We're missing 1 carbon, which is our pH. Just draw that in. Need like a rubber band to keep my sleeve up. Okay, so now the new bond, so I'm going to draw it in red to kind of show that with the same arrow, right? This is the new bond we are creating, right? With a lot of these reactions, I've always noticed people mess up their carbon count, right? Now, if this is something you're going to mess up, I would highly suggest using the numbering system then, right? So let's keep the same numbers here. I'll just use blue here. This was 1, and this is 2, right? 2 attacked 3 on this one, right? So now we have the rest of the structure, right? So this was 3, right? 3, this is going to be O minus here, right? This is the rest of the structure here, right? So this was, let's kind of keep the count. Stop the count. 5. And there you go, right? And that red line represents that arrow for the carbon-carbon attack there, right? And then, obviously, this is why using pencils is nice on your exam. So, you're not kind of writing this stuff set in stone, right? And that is our molecule, right? And like I said, if you have difficulty with this stuff, just do a carbon counting. It'll help you get your product easily, right? And look at the bonding we did. 2 bonded to 3, right? That's the new bond we created, which is bonded to 4, 5, which is bonded to O, right? Obviously, we don't have to show the H, but we know there is an H there, right? And obviously 1, 2 is bonded to the rest of that structure, right? That is now no negative charge because the electrons came down. This has a negative charge because the electrons came up. And that's kind of what the water here is for, right? It's just protonation, right? God damn. How do I show touch keyboard button? Maybe that's what's been causing the keyboard to come up so much. Okay, and then H2O, right like this. And you get your final product, which I have to draw out again. That's okay. Boom. right? So this is a alpha beta. So this is a beta hydroxy aldehyde, right? So if you had a ketone here, you have beta hydroxy ketone, right? So yeah, that's your final product, right? So when you only have, right, let's say if you like, let's say you were given, on like, was it question 3 or 4 on your exams, how you're given, that question with 8 different reactions. Say one of these was just NaOH and H2O, right? Your final product, basically what he's trying to look for is an addition product, right? This. And generally, right, you want to stick to kind of, not really you want to, I would assume you'd probably stick to aldol, like aldehydes, and that's why this is called an aldol addition. You could still do this with ketone, but the issues with ketones, right, is that you have 2 alpha positions. You could have a mixture of products, right? Right, depends on symmetry of your ketone and stuff like that, right? So generally it's done with aldehydes because we know there's only 1 alpha carbon and 1 alpha proton, right? The aldehyde proton is not acidic at all, right? So yeah, that's your final product there, right? And this is just with base and water, right? Let's do another one, but without all this mechanism, right? Because I just wanted to show the mechanism once, but now we could kind of just go straight to products, right? So let's do C because I do not want to draw out more rings. Actually, we'll do D. We have this, and it's asking for an aldol addition product after using base and water, right? So what we could do first, right, is you could draw the enolate version right next to it. I'll draw it in the C- version, right? Right, and now we could do a quick carbon count, right? We'll say this is 1, 2, and then let's say 3 is the methyl here, right? The other part is the ethyl, right? And then we'll say this is what, 4, 4, 5, and 6 is the methyl here, right? So essentially we are trying to create a bond from 2 to 4 here, right? So let me this, right? Basically we're creating this bond, right? That's going to push this up and that's going to eventually get protonated. So our final product, let's start drawing it. Let's try to draw it this way. So H, right? So that's going to be our 1 is connected to 2, which is connected to 3, right? Maybe I should probably put 3 on the bottom. I'm going to put 3 like this, right? So 2 formed a bond to 4, right? So once again, let me keep the labeling. 1, 2, and this is 3, right? And there's an ethyl group attached to 2. We're all good right now. Now we created a 2 to 4 bond. So we could say this is 4, right? 4 is connected to that carbonyl, which we know becomes our OH, right? So we could put this as OH. And now that is 4, right? Which is connected to 5, right? Which has a methyl group and a ethyl group, right? So in terms of numbering, this would be 5 and this would be 6. That would be your, well, let me maybe draw this part a little better. Wrong color. Right, that's how it would look. Kind of a weird looking thing here, but yeah, it's pretty easy to get the thing without, I mean, obviously the mechanism, you could always do it through there, but in terms of doing it quickly, right, is do a quick number count and then see what bond you're creating, right? And then basically know that that bond you're creating, right? So the carbonyl, right, that's being attacked, right? So let's point that out here. The carbonyl being attacked becomes your OH, right? That's kind of the key here, right? The carbonyl being attacked becomes your OH, right? So that's all it really is. Okay, so then let's do one. You guys want to do another mechanism question with the ketones? Okay, so that's 21.15. I was looking at it, so figured let's do an example with the ketone as well. So here we have, it says when each of the following ketones is treated with aqueous sodium hydroxide, the aldol product is obtained in poor yields. In these cases, special distillation techniques are used to increase the yield of aldol product. In each case, predict the aldol addition product that is obtained and propose a mechanism for its formation. Right. So I'm gonna do B because whoa, that thing just spazzed out. Down here. $21.15, and we'll do B. And there's a reason I'm picking B. Actually, the rest of these they're all symmetrical anyways, or there's two of these have symmetry, A and C, and the other. Basically, right, how many alpha protons does this thing have? That's really what important here, right? 1. So in case you are getting products like this, right, let's say you think you might have a crossed aldol product or something like that, if there's like non-symmetry or something, right? Just make sure you check if there are even alpha protons, right? That's very important in itself, right? Is checking if there are even alpha protons, right? It isn't 2, right? The reason it isn't 2, right, is because this, god damn it. Goddamn freaking laptop, yo. There we go. Let me scroll back up. Right? So your 2 alpha positions are this and this. Here you have 2 methyl groups. It's a quaternary center. There's no protons here, right? It's all carbon bonds. Here we have 2 protons. Oh, sorry. I see what you're saying, right? There are 2 protons there. The question I meant to ask is how many alpha positions are there with protons on it? Then it would be 1. But yes, technically you're right. There are 2, right? There are 2 protons here, right? Just to be clear, right? But there's 1 position that has protons. That's kind of what I meant to ask. Kind of jumbled it up there. Okay, so let's do a mechanism, right? Gonna erase the sodium there. For the sake of simplicity, I'm probably gonna use C- form here. You know what? Let's not do that. I remember somebody was always complaining about consistency. Since I already started with the O- form, I'll stick to the O- form. Right, so we get that. Now this reacts with itself. Yeah, I mean, that's assumed though, right? So it's not going to say 2 equivalents, right? But when you're given these kind of conditions, you're assuming you could use, you have like, even if it's not 2 equivalents, right? Let's say it doesn't matter, right? Because if you have 2 or more molecules, you could do this reaction, right? That's kind of like what it is, right? Is that you have your original starting material and you're turning it into 2 things. It's going to act as an electrophile and as a nucleophile, right? So it doesn't matter the equivalence unless you're trying to actually do this in the lab, which I don't think CCNY does in their Oreo lab classes. I don't know if they do a enolate reaction. I don't think they do though. So now this will be another molecule. Call this 1, 2. I guess we'll call the other CH2 group there 3. And we'll call this 4, 5, 6. Then what happens here, right? Electrons push down. This attacks this, pushes this up, right? It's basically the same thing. The only difference now is your final product is going to be a beta hydroxy ketone. Right, so now let's do our count, right? We're forming a bond between 2 and 4 here, right? Even though this is drawn as, the the double bond attacking, we know it's going to be between 2 and 4. So first, let's kind of draw our, I guess, original enolate. This, where the carbonyl remains intact. Looks like this, right? This is 1 and 2, you can mention here. 1, 2, and 3 here. Right now, this is bonded to new bond, right, to our OH. Oops. If we do some labeling, right, we attacked 4, which is connected to 5 and 6, and that's the rest of the ring there, right? And now your final step is simply not deprotonation, protonation. It's your final product. There we go. Right. So final product. Right. Beta hydroxy ketone, right? Because now here we have a ketone, right? So this is alpha beta, right? So that's why beta hydroxy. Pretty straightforward. Like I said, it's the hardest part about this is keeping track of your carbons. I personally think the chemistry itself is easier than the last few chapters here, right? It's the most thing people have difficulty with, like I said, is the, drawing those bonds and then making sure, am I using, my bad, I meant to write it here. We could just reduce that. Did I write a H2O up there too? Yeah, thank you for pointing that out. There would be no acid there. Yep. So there's things to fix in your notes, right? It's HOH, H2O. Okay. All right, so we could just take a break here, I guess. 5 minutes or so. Maybe up to 120, and then we'll do, what is it, what's left? You guys covered until, I should say. So we're going to do condensation questions. We'll do the mechanism and also how to do the products quickly. There's a couple of things you need to know about those, though, because you're forming an alpha beta unsaturated carbonyl. Kind of stereochemistry comes into play there sometimes. Else, and then you guys did crossed aldol. Okay, so we'll do one example of that. It's a good question, 21.19. And did you guys do the Clayson yet? Okay. And you said, oh, yeah, the Deichmann cyclization, right? That's where you guys, I think he also was doing decarboxylation. Where is that? Yeah, that comes in later. I mean, we could always pick that up next time. That's not an issue. Um, yeah, we'll probably just end that Clayson stuff then. Yeah. Okay, so we'll resume at 120. Yeah, so in terms of your exams, I think he already mentioned, right? He said most of the, I mean, I was looking at the answer key the other day. It seemed like most of them were from your textbook, right? So that's why I do the questions in these recitations in between the, because I don't think he assigns that in chapter questions. He does the end of chapter questions, right? So I go over those because those kind of cover all the concepts. So going forward, I don't know if you'll do the same thing again. Probably will though. I mean, I don't know. Um, Make sure you do all those practice suggested problems, right? It can really help you get a good grade on the exam if he plans on using them again, right? Um, but yeah, the average I think was more or less similar to the first exam. Surprisingly, actually higher, but I guess that makes sense because some people probably dropped, which means the people left in the class are still doing well. So that trend will probably continue for your third exam, right? Is usually the third exams have less of a curve too, is because at that point, a good amount of people who know they weren't going to get a good grade. I have no clue if he's curving or not for exam two. That's something you should ask him next week. Um, but usually for exam three, the curve goes down even more, right? Because the people left in the class at that point are doing well, right? So everyone usually does well, better on the exam, which means the average should be higher. We'll see what happens. I mean, I don't know what will happen. Things can always change. That's generally the trend, right? Is the first exam is okay, right? The second exam is by far the hardest, right? And then he does not drop the final, right? So you guys could read the syllabus, I'm pretty sure. So he drops one of the midterms. He drops one of the midterms for like one of your first three exams, right? One of those midterms. The final is mandatory, which I personally like, right? I mean, the thing is, I would do that policy too, but I would also do another policy where if you get a 90, like not like a mixture of 90s, like let's say you had an 88 or if you had a 90 plus on all three exams, then you've demonstrated you learned everything, right? And I'd let you do that, which is I think Salami and India do that. Um, but at the same time, the reason I would want to make a final mandatory is because it really tests if you actually, remembered all this stuff at the end of the semester, right? Which is why I don't mind that finals are mandatory because it really kind of lets, in terms of the institution that that class did a proper job in representing, the course outcomes, I guess, right? So the final is mandatory. There's only grade is dropped. It's your lowest exam grade, right? I don't know how much each thing is weighed. Maybe it's all equal, maybe it's different, right? But your syllabus has all your stuff for like A plus, A minus, A, all that stuff. Average for this exam was like around a 60. Yeah. So I don't know what the average for the first exam was. I want to say like 58 or something like that. Um, so this one was slightly higher. Yeah. It was 52 for exam one. Give me a second. He said it was 52 for exam one. Because the thing is, then I'd assume he's probably taking outliers out or something like that. Let me just check. I can just check. Okay, yeah. So then it's probably data that he didn't like upload here. So you'd have to ask him for the exact average. I don't know it. What I see on Blackboard is it's within a margin of error. It's just slightly different. Just because the way Blackboard accounts for certain grades, it like tallies it up. So I'm assuming the values here are skewed improperly, right? Did he say how much the curve on the first exam was? Oh, to 13. Makes sense, I guess. Something like that. He said 10 points. He said 10 to 14 points. Okay, so you probably get a similar curve for this exam, I would assume. I mean, honestly, these were so similar. I wouldn't know which one. Like I said, you could ask him on Tuesday what the exact average was. Um, but I mean, the one thing I did notice was the people who I mean, I was kind of just looking at, so like, for Zoom, you could look at usage statistics, right? So like all these sessions I have, I can see how many people joined, how long you guys were in here and stuff. Not that, attendance is mandatory here or anything, right? It's perfectly fine, but like I think for the most part, people who've been attending recitations have been, I mean, looks like, I mean, I just kind of quickly looked over the grades and then looked at usage rates and stuff. It seems like, I mean, I'd like to hope that recitation is helping people. And it seems like that's for the most part the general trend. But I mean, it also comes out to thing. It's just like there's only so much professor can do, only so much I can do in terms of, helping you guys, right? In the end, it comes down to you studying and being able to actually do well on the exams, right? Um, I just like to hope that, hopefully this was useful to you guys and might be useful in the future. Yeah, I'm assuming there's probably going to be a few more people who drop it now because I think that what's the withdrawal date for the semester? I forget. I know in the pandemic they changed that thing, right? Uh, like they made like I remember way back in the day, withdrawals used to be pretty early in the semester, like after your first exam or something. But now I think it's pretty late in the semester where you could withdraw. I forgot what it is, but I think you could wait until your third exam afterwards to see if you want to withdraw or not. Um, Not that I'm suggesting for anyone to withdraw. I'm just kind of mentioning that. Give me a minute. I'm just kind of curious as to the CCNY policy. Oh, no, I guess, oh wait, no, yeah, it is. Here you go. Is it December 13th? Last day to withdraw from a class with the grade of W. Yeah. Okay, so I don't know when your final exam is. Let's go take a look at that. Let's go syllabus. Final exam is December 19th. So, I mean, I guess you still have like the weekend to decide if you want to withdraw or not. Um, Hopefully, I mean, I think everyone here is doing relatively well. I didn't really look at each specific grade too much, but yeah, there's some time in between the third exam and your thing. So that's kind of nice. They improved the withdrawal date for current students. I always thought it was unfair to have it a little early like that because you don't know, like, especially, people's circumstances always change. So you can't kind of predict that stuff. But at the same time, you don't want people getting a lot of withdrawals because that kind of takes away from the integrity of the college. Okay, let's get back to the chemistry, I guess. Okay, so aldol condensations. There are examples of these. 21.17. Surprisingly, this session has gone pretty smoothly in terms of the writing. It was an absolute nightmare for Orgo 1 on Thursday. But I guess this new stylus just works better. Still, I miss my surface. Okay, so here we have draw the condensation product obtained when each of the following compounds is heated in the presence of aqueous sodium hydroxide. Okay. So let's draw the first one, which has a lot of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's our carbonyl. It's our aldehyde. And it basically said NaOH, H2O, and we have heat, right? So the beginning of this process is just an aldol addition, right? So really all a condensation is an aldol addition. Oh, you guys did do E1cb, right? Because this is, yeah, because E1cb comes up in this, right? I always forgot what part of the chapter. Yeah, so you guys did do the E1cb mechanism, which we'll talk about when we do this. Probably mentioned it. I just assumed that maybe just forgot, but it's fine. Okay, let's do the mechanism for this, and then we'll do product outcomes for like two or three of these, because it's actually very easy to get the products for this. There's a nice little trick in the book that it shows you. So let's say this. Get our deprotonation stuff going on here. But I'm gonna go down this way. Right, scrolling over. Okay, so now we have our enolate. Oh, sorry, I meant to draw it in the other form. Right, so we have our enolate. That's a little better. Annoys me. Now it's going to react with itself. So draw this here. 1, 2, 3, 4, and 5. Right. Draw the next set of arrows. Push down. It's going to push up. Right. We are forming a new bond between carbon to carbon. Right. And now if we draw our product here, I'm just going to keep going downwards. It's just easier to scroll up and down right now. Okay, so let's try to draw this. Oh, is this an H? My bad. Let's make sure I had it up here too. Yep, okay. I draw this like 1, 2, 1, 2, 3, 4, 5. We create a bond from 2 here to our next thing, right? So this is just your typical aldol addition part, which we did earlier. At this point, I'm not going to do the numbering anymore, right? You guys can do it on your own. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Next step. This way. The protonation of your minus. Whoa. What the fuck did that happen? Sorry. What language? Give me a second. Just literally rotated the screen. I don't know how that happened. Okay. Apparently the taskbar was not locked. Okay. The screen should be fine on your guys' end, right? There's no like not flipped or anything, right? Okay, cool. I don't know. It's bugged out here. Okay, back to this. And now we get our beta hydroxy aldehyde. Sorry, yeah, beta hydroxy aldehyde. So that is the addition product. But we are not going to stop here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is our OH, right? This is where the heat is going to come in, right? Is basically we have enough energy to keep going forward, right? And now we have a, and this is a very different mechanism than what you guys have seen before, right? In terms of kind of the nature of the mechanism. That's why it's classified as E1cb and not an E1, right? Because E1 goes through a positive, some sort of like, carbocation intermediate. This goes through a carbanion, right? So we call it E1 conjugate base, right? So what happens here now is another molecule of your base is going to come in. Let's draw it this way. So we have OH minus, right? And now this is very important for this mechanism. This is the difference between the alpha halogenation and this, right? The alpha halogenation proceeded through a E2 mechanism, right? It was concerted, right? The, what is it? I guess it was the water came in, grabbed a thing, grabbed the proton, created a double bond, kicked, right? It was all an E2 concerted mechanism. This, you need to show the carbanion if you are given a mechanism like this, or if you're asked to, I don't know, some problem where you had to do an aldol condensation, you have to show that mechanism. Make sure you draw that carbanion, because otherwise that means you didn't understand the mechanism, right? This was something that forms, right? Because they were able, detect it or trap it to prove that it went through this mechanism. So H, say that one. Try not to scroll. Or grab this, and this goes here, and now we have a carbanion that looks oh. Well, it forms a carbanion, right? And then it makes then basically the lone pair turns into a double bond, kicks the OH, right? So let's say put the negative here, right? So let's say 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. This is OH. I actually put this over here. No matter which side, it's just easier to draw the arrow when it's on the. Right. So now we have this carbanion, right? And now what happens here, right, is generally, right, we want leaving groups when they leave not to be reactive, right? But you guys learned this in your lecture probably. This is one of the few times where OH is a great leaving group, right? Or a base or something that's going to become a very strong base, right? And basically very reactive. It's a good leaving group. And the reason being is because kind of think about the kind of conditions we're in. We're in highly basic conditions. So it's okay to kick off an OH because we have we have an abundance of OH minus. This is kind of similar. You're going to see chemistry similar to this in the amine chapter, where you can kick off an NH2 group under basic conditions, right? That's going to be I think it's this like silver mediated or something, Hoffman elimination of alkenes or something like that. But there are cases where you can kick off, what we consider bad leaving groups like NH2 or OH, right? And generally those are under basic conditions because, when you kick them off, they're going to be similar in reactivity to everything else present, right? Now, if we did this in something like water or acidic conditions, it wouldn't make sense because as soon as it kicks off, it's going to attack our acid, right? Or deprotonate our acid, right? So this is why, because it's all about thinking about your reaction medium. We are in conditions that allow for this. Normally, this would never happen, but because we are in such basic conditions with abundance of OH minus, we can't do this, right? So now the next arrows, right, this is why this whole second step is two parts, right? The first step is the deprotonation. The second step is the formation of your double bond, right? Your loss of leaving group, whatever you want to call it, right? So they are stepwise, and that's why it's an E1 mechanism, right? It's like an E1 mechanism, the difference being it's anionic in nature as opposed to cationic. Here, this here, right? And we have a final product that is going to look like, whoops. Yep. Let's draw this out. Okay, is that the final product? Okay. Yeah, but let's think about one thing here though, right? In terms of, I guess, the stereochemistry of that double bond there. I mean, technically it is. Well, the thing is, technically, this is the trans product or this the E product, right? Because if we look at it in terms of carbons, right, this is the large group here and this is the large group here, and they're opposite to each other. So this is E, right? So it doesn't really, it's not. That's why I don't want to use stereochemistry descriptors. It's more has to do with steric interactions, right? Think about this as a gigantic group in itself, right? You have a large amount of electron density here. Oh, shoot. Let's try to undo that. Right, is you have this gigantic group of electron density, right? Then you have this gigantic group of electron density. You're going to have repulsions, right? And that's why it's important in terms of your final product to make sure your, what's it called? I guess where your double bond ends up, you create trans, no, that's why I don't want to use trans. Basically, the R groups are trans to each other. So there might be cases, I guess, technically where that you might have the aldehyde trans, but in this case, you have a, what is it, 1, 2, 3. So you have a propyl group and a butyl group, right? So those are going to have steric interactions. So this was not the final product, right? The final product looked like this. second. 1, 1, 2, 3, 4, 5. There we go. That's your final product. So no, there's no resonation or anything, right? And what's the kind of the, in case you're asked this, or this is something you might have to explain on your exam, or honestly, it's just good to think about, what's the driving force of this reaction? Think about this. Why don't we just stop at the addition? Why, when we have enough energy, why do we go to this final product? And if you kind of, kind of point out this part here. It doesn't have to do with acidity. pKa kind of, maybe, I don't know. But it has to do with something else, which you guys learned in the beginning of the semester. Something that gives stabilizing effects to molecules when they have multiple double bonds. Kind of giving away the answer here. Hopefully someone can see it in your final product. There you go, bing, bing, bing. Conjugated pi systems. This is one of the driving forces of condensation reactions, is you're forming this conjugated pi system. It's an extremely stabilizing effect. And that's why when you have enough energy, it's not going to you're never going to get an addition product. Any addition product you get will just always be converted into the final alpha beta unsaturated ketone or aldehyde, right? The reason being is because you're forming a conjugated pi system, which has really good stabilizing effects, right? So that's the driving force of this reaction, right? So yeah, when it's heated, right? So high energy, high temperature, however you want to consider that, right? So yeah, in terms of, I guess, if you have to, think about that, like, if he likes asking theoretical questions like that. So just think about stuff like that. What can cause a reaction to go forward? One thing is usually exploitation of Le Chatelier's principles or some sort of stabilizing effect, right? That's why all this stuff keeps coming back together. It's important to understand why things happen in a certain way. Okay, so now let's say, what if we wanted to do this without, I wanted to show the mechanism once of an aldol condensation. What if, how the question asked you, right? Was to just get the product, right? How do you do that quickly, right? And that can also help on your exam. Is I want to show you it once here, and then we'll do a couple more practice examples. So we had this here, 1, 2, 1, 2, 3, 4, 5. H, right? And what you can do is, so for a condensation process, this is kind of a nice trick in terms of how you can get the product kind of easily, right? Is if you line, so you're going to have two molecules of this basically, right? This is your alpha position, right here, right? So then what you could do is you could line up another same molecule, right? And we could do it in the same way, just for the sake, right? And essentially where this carbonyl is, right, is kind of where this double bond is. So essentially you're forming a double bond right here, right? And now I could do this, right? That's a product, right? I don't have to show this H, right? The only difference is you have to just, remember, consider steric interactions. So the only thing I would change here is that the R group is far away from each other. We could draw it 1, 1, 2, 3, 4, 5. Boom. So the condensations, it's actually very easy to get the products, right? Because you could do this little trick where you line up the carbonyl with the alpha position and then just literally change that into a double bond, right? So let's do the same thing for the next question, kind of to re-illustrate that point in case it might have not set in. Let's do C. Right, so we have an aldehyde that looks like This is a cyclopentyl group, right? And now we want to get a condensation product, right? So what you could do here is draw another one of this molecule, right? The only difference I will do here, right, is remember, I want to consider steric interaction, so I'm just going to draw it the other way, right? Just to account for my steric interactions there. Right? This is our H, right? And now this is our alpha position. This is where our carbonyl is, and that is where our double bond will form. So we could just draw this as a double bond. And everything's in the right place where the large kind of groups are away from each other to prevent any steric interactions. You don't even have to show the H. Just like that, you got your final product. It's a nice little trick that could maybe save you some time on your exam. The book actually shows it in the solutions manual, I think. And I think also the second language book shows it, right? So it's a quick way to get your products for these kind of questions, right? Let's do another one. Let's do some ketones here. Yeah, I'll do it with the next one here, right? So I'm going to redraw everything. Ooh, 1, 2, 3 carbons on each. Right? So this is only for condensation products. This kind of works, right? So we have our thing here, right? So I'm going to redraw this. This is our starting material, right? So in order to get your product, you can draw your original starting material just as is, right? And is this symmetrical, unsymmetrical? Symmetrical. So does it matter which alpha position we choose? Nope. Right? So you could line it up to either ones. It doesn't matter. And because you have two R groups that are identical, it really makes no difference whether there's going to be no stereochem in terms of the double bond here, right? So I could line it up here. I could line it up here. So now I take another molecule of the same thing and I line it up with one of the alpha positions, right? So this is where our carbonyl is. Now we draw our groups. 2, 1, 2, 3, right? So we drew it up here. So it's lined up with this alpha position. Oh my God, this goddamn computer. Oh my Jesus Christ. Okay, let's go back to using the sleeve. Right, that's our alpha position. This is our carbonyl, right? And now essentially what you can do is you line them up like this, and that becomes your double bond, right? So then your final product, right, is just this, right? And if you did the whole mechanism and reactions, you're going to see you get that. And this double bond, does it have any stereochemistry? Kind of drew this line. No, right? Because we have two identical propyl groups there. So steric stuff doesn't really make a difference here, right? That's a kind of quick way to get that product for these condensations. So I like the condensations, in my opinion, are easier than the additions, right? Because the additions, you kind of still have to draw the enolate and then do the kind of bond thing to see where you get it. But this one, you could kind of just line them up and convert the carbonyl into a double bond, and that's your final product, right? I think it's a pretty cool trick. Let's do one more example. Why not? Let's do B, an aldehyde. It's tertiary. Yeah, it is. Okay. And same thing, NaOH, H2O, delta. Right, so let's redraw our aldehyde. Good. right? Now we could draw our carbonyl under here, right? Now the R group, am I going to draw it off to the left side or the right side here in order to get the best major product? Right side, right? We want to avoid steric interactions, right? So just make sure you draw it properly, but on the other side. So it's 1, 2, 3 carbons until you have the 3 methyls. So 1, oh wait, sorry. 1, 2, 3. So 1, 2, 3. There, right? And now this carbonyl, this turns into your boom, final product. Right? Hopefully that can help you guys with some of these questions, right? Little tips and tricks like that. Obviously, if you have to do a mechanism, you got to do the mechanism. But if you are asked for just a product, hopefully that can save you a good amount of time. Maybe you could focus on other stuff on your exam, right? That is an H. That is correct. So here, I can just erase this, right? Thank you for pointing that out. Yeah, so that's the final product. There's no methyl group there. Okay, let's do an example of a crossed aldol and probably have time to do Clayson. I just have to stop at Clayson. Ooh, actually, I want to do this example too, is an intramolecular aldol. Those are nice too. Oh wait, did we get to those? You guys did what? Did you guys do an example of that? Yes. All right, cool. So we'll do an example. Did you guys do the one with pentinone, I guess? I would hope it's not the most simple example, or like something like this. I'll try to see if there's another example. I don't want to repeat exactly what you did in your lecture, right? Okay, so let's do crossed aldol additions, right? So all of these were either with aldehydes, so that those just had one alpha position, right? Or symmetrical ketones, right? But what if you had multiple aldehydes coming together or multiple ketones, right? Then you could kind of, you're going to have a lot of basically different products you can get out of that, right? So these are going to be crossed aldol additions, right? Let's start with B. Right? So basically it asks you that this is a final aldol addition product or aldol condensation product, and it wants you to kind of give possible starting materials, right, that you can use to create those. So we're kind of going backwards, right? But it's a good kind of exercise for this stuff. It's a horribly drawn cyclohexyl ring, but maybe you guys will let it slide. Okay, so if I labeled all these carbons, right, which is the bond that we have to cleave is really what I'm wondering, is what I'm asking. So I'm going to label all of these blue. So I was doing that before. Right? What bond, right, between which two atoms, which two numbers, right, is the one that was formed between two different carbonyls? Good, right? 2 to 3, right? Because this is why identifying the product can be useful, right? Because this, this is a beta. So if this is our carbonyl, this is alpha, this is beta. So this is a beta hydroxy ketone, right? So in this case, we know that the bond between the alpha position and where the OH group is the one that we created as a result of an aldol addition. So the first thing we can do, holy shit, menus and menus and menus just keep popping up. Yeah, unfortunately, unless I get one before Black Friday, the next few recitations are probably going to be like this. So next week we'll have recitation, but the week of Thanksgiving we won't, right? I'm not going to be in town anyways. I'm actually going to Milwaukee for visit family, and then there's a wedding in Chicago. So that week we won't have any recitation regardless. Okay, so we could just cleave this bond, right? Let's do that. And now you can kind of see what kind of created this. So one, we have a ketone that looks like this. Oh, you know what? Let me leave that here. And I'll just draw an X over it. So basically this, right, originated from cyclopentanone, I guess it would be called. So cyclopentanone, right? And then the other one, was the other one an aldehyde or a ketone? Where 3 is. Think about what's attached to 3. Should be pretty straightforward, right? If this was our carbonyl, is this going to be an aldehyde or a ketone here on this right side? So it's attached here, right? Is if we cleave this bond here, right? Maybe it'll be easier to see when it's cleaved, right? This here, this is removed, right? So if there was another R group there, so it was 2 R groups at the OH position, right? Then yes, right? You would have a ketone, but because there is no other R group directly there, it's an aldehyde it would start from. So this was basically a crossed aldol between an aldehyde and a ketone, right? So our two products look like this plus there we go. Right. Let's do another one. Let's do one with uh condensation product. Let you guys actually take a minute to try this. Just kind of think about what we did earlier, and you can work backwards, right? So this is a condensation product that we have here. And this is actually a very good condensation product, right? Why is this one really good? This will probably form in almost probably nearly 100%. Not 100, but like definitely over 90% yield easily. Can anyone kind of think about why? Well, anyways, take a minute to do the problem or so, right? To separate this into the original starting material, right? But the answer to that is that there's even more pi conjugation because of this phenyl ring, right? So this is like basically what in this addition product would never, you it would be almost impossible to isolate it, right? Because it will just turn into what's it called? This conjugated pi system. Hopefully everyone got it right. But remember, we said this double bond here, right? When we have a condensation product, right, is where essentially the double bond of the other one came from, right? So this one was actually very easy. Those are, just gonna leave it like this, was our original product. So we had benzaldehyde and cyclopentanone here, right? I don't know if you'll get a question like this because he did do that on the last exam, right? He did that hydrolysis question where he gave you that gigantic macromolecule. And then basically we did a practice of that in our review session. You had examples of that in both your practice, maybe 3 of your practice exams, right? So I would like to hope everyone did that well. There's a reason I spent a lot of time on the hydrolysis stuff, right? So I know he asked a question similar to this, right? That's why I wanted to do this exercise, is going back, understanding, going backwards, I guess kind of important too, right? So yeah, those are your 2 products. Okay, we'll probably end on here. This is going to be I don't think we're going to probably have to start with Clason's next week because I don't want to just jump into them and just do one example. So we'll probably let's just end with a intramolecular process here. So let me see which one of these I want to do. Okay, so we'll do 21.23. Oops. 21.23, right? And it basically said when 2,6-heptane dione, right? So 2,6, right? So first heptane, right? So 1, 2, 3, 4, 5, 6, and 7, right? And it says 2,6 dione. So that means at basically the second to last positions on each end. So it would should look like this. God damn it. Sorry. And this, right? That's your molecule, right? Is heated in the presence of aqueous sodium hydroxide, a condensation product with a 6-membered ring is obtained, right? Draw the product and show a mechanism, right? So basically it's saying that NaOH, H2O, and heat, right? You form some sort of 6-membered ring, right? We're just going to leave it, some sort of 6-membered ring, right? And it has that. No, I'm not going to give away the final product, but so it says what does this say? It says draw the product and show mechanism for formation. So we could actually draw the product first. We'll start with that, right? And then we'll just go into a mechanism because that's usually how a mechanism question is asked anyways, is you need to see the product so you see what you're getting, right? So if this is a condensation, right, essentially, right, we can say that if we kind of conform this, right? So this would be like, what is it? You know what? Let's start with the mechanism. I just realized it's going to be confusing for you guys if we did the product first. Okay, so first of all, let's do a carbon count, right? If we did 1, 2, 3, 4, 5, 6, and 7. Okay, so we have how many alpha positions here since we have 2 carbonyls? 4, right? So we have, 1 and 3 and 5 and 7, right? If we wanted a 6-membered ring, right? So this is kind of what can give you insight to the mechanism, right? Is if we wanted a 6-membered ring, right, we'd have to do a bond between, what is it? Can we do a bond between 3 and 5? That's not a 3 and 5. It would be, can we do a bond between 3 and 6? Right? So if we did 3 and 6, it would be, the ring would be 3, 4, 5, and 6. So it would be a 4-membered ring, right? Same thing if we did 5 to 2, right? It would be a 4-membered ring. But if we did 1 to 6, then we have obviously 6 atoms in there. 1, 2, 3, 4, 5, 6. Or if we did 7 to 2, right? And because this is symmetrical, it doesn't matter which side you pick, right? I'm just gonna, I guess I'll start on the left side. So we'll draw OH here. Oops, let's draw that in white. Draw this H here. And let's start with the mechanism, right? So we're going to form our enolate, right? I'm going to draw it in the regular form here, C- form. And now we get all right, so we have our enolate, and we have our other carbonyl already in the same molecule. Obviously, we know this is intramolecular because the question said it, right? So we're going for a 6-membered ring, and now it's just going to be an intramolecular aldol addition type thing happening here, right? That's going to kick up, and then you get your next intermediate. This is where carbon counting, it's again, can be useful. So we did a bond from 1 to 6, right? So 2 is going to be our original carbonyl, right? So let's say, whoops. So if this was, let's mark these, this is 1, this is 2, and the rest of the ring would be here, right? 3, 4, 5, 6, right? And 6 is bonded to 7, right? So this is now the bond we created. Just to kind of clarify, I'm going to draw it red. I'm going to change it to white later, right? But just to kind of show you what happened here, right? Then I'll label these again too. 4, 5, 6, and 7. It's actually our O minus, right? So everything's in place, right? We did a bond from 1 to 6. Let me zoom out a little, right? We did that bond from 1 to 6, right? 1 is connected to 2, 3, 4, 5, which is all in between, which makes sense. We're forming a ring now. 6 had 7 attached to it, the methyl group, and the O minus, right? Which was the carbonyl that turned into O minus. Now we do a protonation, right? Because at the carbon counting, I've taught this in Orgo 1, I've taught this in Orgo 2. It can really help on your exams if you're having trouble, right? It's, obviously time managed, but if you have enough time to do it, right, you can kind of basically always confirm you're going to get the right answer. Right, now we have a protonation occur. Whoops, oh my God. And we are forming a ring with the OH at the beta position. Okay, and now, sure I did this right. Yeah, okay, should be fine. You know what, maybe for simplicity's sake, I'm just gonna flip these groups just because it's easier to draw the OH here, right? Just for now, I'm just flipping these. Just everyone good on that, right? All I did was change them. Doesn't affect the molecule anyway, right? Technically, that is a chiral center though, but we're not showing wedges or dashes, so it doesn't matter whether OH is there. It's just that for the next step, it's going to be easier for me to kick it off this way. All right, so now the next step is E1cb, right? That's the condensation part now, right? So we have another molecule of base. Let's go downwards, return, right? So OH minus is going to come in again. Whoops, just draw the H here. Right, remember this is a stepwise mechanism, so it's going to come in, grab this. You're going to form your carbanion first. We get our conjugate base or carbanion, whatever you want to call it. Right, that's where our carbanion is now. And now the final step is kicking off OH, forming our double bond. Make that alpha beta unsaturated ketone. And boom. And we get your final product, which is a 6-membered ring that has a alkene in it, and it is tri-substituted. And there's stereochemistry, it doesn't matter because it's locked into the ring, right? So your final product looks like this. And the methyl group sticking out. Okay, so that's an example of an intramolecular aldol addition, in case you get something like that. Okay, so we're gonna end it off here, right? Probably start with Claysons, and I'll probably end up finishing the rest of the chapter next week. I don't know if you guys will start amines by next week. Maybe you will. I don't know. We might do that too towards the end of the recitation, but we'll probably just focus on the Clayson, and like, you know, you're gonna learn something called quite a few things here. There's malonic ester synthesis, acetoacidic synthesis, it's alkylations, Clayson stuff, and then Michael additions. So there's quite a few things still left. Okay, I'll stop the recording here.